Hello everyone. Previously in lesson 8 I talked about test concerning variances, single variance, and then if we are comparing two. Today I would like to talk about goodness of fit test and then test for independence. So the main objective in the hypothesis is that if we already, let's say we are assuming that from a population we are collecting some data set, and then we are saying that it follows some distribution. Is it going to be true? Is it really going to follow that specific distribution or not? Using a sample, we are going to test that. And it could follow geometric distribution, Poisson distribution, normal distribution, depending on what kind of distribution we would like to test. But test will follow specific rule, and then we can only do that using the chi-square test. So that's what I would like to show you. The last one is that we would like to see if we have two factors or two variables, and then we collected information for those two variables in a population, and then we have the sample data. Then we would like to see whether those two variables are actually independent or not. The two events we have. So that's what I would like to show you. So let's go to the detail on the page, and let's go to goodness of fit test. So in the goodness of fit test, since I mentioned to you that I'm going to talk about if we generally believe that a distribution is Poisson distribution based on the data set we have, or maybe from the popular belief, or we assume that, then we would like to test it whether it's actually following that distribution. So you can see that we are given an example. That's the example I would like to show you in detail. I would like to show you in Excel. So at first we need to define what we have in the example. So you can see that we are talking about Poisson distribution. That means we want to test whether the data set follows Poisson distribution or not. And then we have 100 plots, and we have the data set. So in the data set we have number of trees with some infestation, and then number of plots we observed. Basically we want to find what are the expected value for each of these observed value. That's the main interest. To do that, at first we need to know how many samples we have. We have 100 samples, and then we will be using chi-square distribution. So in the chi-square distribution, basically you will see that, let me show you, the observed value minus the expected value, and then take the square and then divide by that expected value, and if you sum them, then you will get the chi-square value, the test statistic value. And you know, from the one sample test, when we were testing the single variance, we also use the chi-square test. So you can use the chi-square table to find the critical value. So let's see how we can find the observed, and how we can define the observed, how we can define the expected. So after observed values are basically given in the question, only we need to find the expected value. Okay, so I actually copied this table and put it into an Excel table. Let me show you that. So you can see that I copied the table. So we have the number of trees with infestation, and we have number of observed values. That means we have the observed values. How many classes we have? So you can see that we have 6 classes right now. And then at first you need to define what you actually got from the example. That means what's mentioned in the question. So you can see sample size was 100, and then if you add them, then you will see that the total number of plots is 100. That means that's the sample size. The hypothesis we are testing is that the data follows a Poisson distribution, and then we say that the alternative hypothesis that the data do not follow, that means it's not going to follow, it should follow do not follow a Poisson distribution. And then for Poisson distribution, then the distribution form we have is this one. So over here you can see that we need to have mean, and then for finding the mean we also need to use this total sample size. And then level of significance, if it's mentioned in the question, then you can use the words mentioned, or you can use the level of significance 0.05. So what I did in here, you can see that I created another table. So in that table I copied the data set, and then step for finding mean, that means in this Poisson distribution, at first we need to find the mean. To find the mean from the frequency distribution, maybe you remember that. So all we need to do, consider this this is as a mean value, and then this is as a frequency. You can consider that because we have groups, and then we multiply the numbers of trees and then number of plots, because we are considering that these are the midpoint values. And after I multiply that, just like frequency distribution table, then you will see that for the last one, what you can use 5. I just use greater than or equal 5, so I just use the value 5. And then if I sum them, so I sum them, the sum of fi xi, I sum them, and then you can see that I got it's 200. So whenever we try to find the mean, all you need to do is to sum these what you got, and then total sample size. So I found that mean is 2. We only need that mean, also we need the total sample size 100. And then for each of those groups, all we need to find is the probability value. To find the probability value, you only need to use this equation. So in this equation, all you need to plug in is what's the mean. For each of those values, the mean is same, is constant. So you can use the constant value. The mean is 2. So every time I use mean, that means expectation negative 2, and then multiplied by 2 power x value. 2 power x value, that's what I used. And then for each of them, I've used the equation. I said expectation minus 2, and then 2 power the x value. X value is 2 in here, divided by factorial x. So you can use your calculator. And then for the last one, you can see that for the last one, I said I'm going to use the 1 minus sum of the previous ones, because you will see that it's it should, if you add all the probability, it should add up to 1, but it's not going to add up to 1 if we are not using the 1 minus sum of the previous one. That's why I calculated up to here, and then for the last one I said 1 minus of that, because you are not going to use 5, you are going to use more than 5 as well, because we are only considering 5. So all I did is that I also included the other probabilities in here, so that I can get the total probability 1. And then the expected value would be probability multiplied by the sample size. So you can see for each probability I multiplied by sample size 100, or the total frequency, and then I got for each of them the expected value. So we found our observed value, we found our expected value. Now we just need to use this formula. So in this formula, we try to see observed minus expected, and then square, and then you can see, oops. So you can see that observed minus expected whole square, and then divided by expected. So I found that for each of them, I found this one. After that, I sum them. So let me sum of them, and then the sum is 1.57. In any time you will see, if you see that expected value is less than 5 in any group, then you have to combine the closest ones. So let's say this is less than 5, then you can combine with the previous one, or this is 5 and then you can combine with the next one, so that you get always more than 5. After that, so you can see that we have 6 groups. So the degrees of freedom will be number of groups minus the parameters. So in the Poisson distribution, I told you before, we are using mean and then sample size, those 2 values. So that's why the parameters, 2 parameters we use, and then that's why it's 6 minus 2. And then if you go back to chi-square table, then you will see that for the one-sided test, so you can see that level of significance is 0.05. If you go to the chi-square table, you can do 6 minus 2 is 4. That means 4 degrees of freedom, 0.05. Level of significance, the value you need to find is 0.95. Let me go take you there. So you can see that for in the chi-square distribution, for 4 degrees of freedom and then 0.95, that's the level of because we are going to use the lower region, and then you can see the 0.95 is 9.49. That's the one we are going to use, and then I use that one, and I compared it with the test statistic value. The statistic value is coming from this table. This is 1.57, and then if you compare that, let's draw in here. Okay, so if I draw the chi-square distribution, and then we are looking at the 9.49, so the rejection region is on here, 9.49, and then the level of significance, so this is the 0.05 region, so that's our critical region. And then if anything falls within here, then we are going to reject that. But in our case, we have 1.57, so 1.57 will be somewhere here. So that means it's actually not falling in the critical region, it's falling in the acceptance region. That's why we cannot reject the null hypothesis. So you can see that that's why I say that fail to reject the null hypothesis, so that we cannot say that the number of trees with mistletoe infestation per plot does not follow a Poisson distribution. So that's how step by step you can perform a goodness of fit test. So you will see that in the lesson and in my Excel example, the values might vary a little, but then again it will be close because the approximate value we used, and then you can see that I used the more decimals I used. That's why the values might be a little bit different. So we have another example. Let me show you the other example we have. So you can see that right now we are talking about over here is the normal distribution. So in a 10-year-old poplar plantation, the diameter at breast height outside bark was measured on 200 samples. That means sample size we have n, small n. And then the DBH classes is given over here, and then the observed values we have. So we would like to know whether the data set follow normal distribution or not. Same thing for the previous example as well. You will see that my value and the value shown in this example will little bit vary. So let's copy everything over an Excel. You can use your calculator. This is totally fine if you use calculator. So you can see that I write down the all the values I found from the question, and the sample size is 200. But if you sum them, you will see that these are 200 because number of observed frequency. At first I write down the hypothesis follows a normal distribution. Then I say that it do not follow normal distribution, and we have to standardize it. So that's why for each of the class boundary, we usually use the upper class boundary. The upper class boundary we have minus the mean and then standard deviation. We have to divide by that. That's the Z statistic. Therefore, the standard normal distribution, you know, the Z statistic we will follow is this one. So that means we need three things: the upper class boundary, mean, and standard deviation. So at first I will show you how you can find mean and standard deviation. This is same thing you did for the frequency distribution table, but then again let's show you again. So you can see that I write down the DBH classes. So you can think about, because this is only giving us one value, not the entire limit, the class limits. So we can think about these are the mid values, and then we have the observed values. So you can see that what I did, I actually took the mid value. So you can see that I used these values and think about they are the midpoint in the interval for each class. First one I used 15 multiplied by 8, and then same thing I did for the other one, 16 multiplied by the observed, that means the frequency we have. For the last one you can see that I multiplied 24 by the number of frequencies, and then I have the frequency multiplied by the midpoint. Then you can see that you can sum them, and then after you sum them, then you can divide by how many frequency you have. So that's how I found what's the mean. Similarly, you can find using the frequency distribution how you calculated the standard deviation or the variance. You can do that. So what I did is that I took the square of these values. So you can see that the frequency multiplied by what's the value we have, and then that means the mid value square. Same thing, the frequency multiplied by midpoint square, and then I sum them. So after that what I did is that did the calculation for the frequency for finding the standard deviation. So I just use this value, the sum of them, and then minus the you can see that minus the FM, that means the frequency multiplied by midpoint, square them, divided by sample size, and all divided by, so you can see all divided by n minus 1. And then since I'm using the standard deviation, so I just took the square root. You can say SQRT in Excel, or you can use the power 0.05. So that's how I found the standard deviation. If you are not sure, go back to the first assignment or the lesson 2, and then you will see that how you calculated the frequency, using the frequency, how you calculated the standard deviation or mean. Then you have to calculate the what's the class boundary, because it's not given. So we think about that class boundaries. You can see if it is 15, then we can go for 14.5 to 15.5, and then similarly I use the other ones. You can see that for these midpoints, and then we need to find basically the Z value for the upper class limits, but I also showed you how you can find for lower class limits, class boundaries. So you can see that for the upper class boundaries, all I did is that I took the upper class limit boundary and then minus mean divided by standard deviation, so that I can find the Z value for each of the upper class boundary. So after that, after getting the Z values, I went back to the Z table, and then in the Z table, so you can see negative 1.83. If you go to the Z table, so negative 1.83 would be 0.336. So that means I use the Z table so that I can find the Z probability for each of those values. That's how I found. For the last one, you can also find that, but you will see that when I calculated the probability, because we are going to find the using the limits, that means less than 15 in between these two values, what would be the probability. So that's why I use the same value what we have in the upper class, but for the next one, all you need to do is to subtract them from the next one to the previous one. That's how I found. So you can see the for 0.4129, the probability I found minus 0.2236, because we are trying to find the probability in between these two interval. That means within these two values, what would be the probability. That's what I try to find. And then for the last one, you don't need to find that. All you can do is what's the sum of this probability, and then since this is more than 24, that means everything else I'm counting in there. So 1 minus sum of the previous one. And then the next step is really easy. So you can see that if you multiply by the probability you found by the sample size, so you can see for each of them I multiplied by the sample size, and then I found the expected values. So you can see over here the last two, the probability we found, and then the expected value we found. So you can see that they are a little bit smaller. That means not more than 5. So I just add them together. So I found it, and I actually showed you in here. So I just added them. Then similarly, like the previous example, I just took the observed minus expected whole square. And then for the last one, you can see observed minus expected, but the observed value should be sum of these two, because we combine the class. And then we found similarly I found them, and then sum them. It will be a little bit different value in the lesson, because I use the more decimals. So you can see using the chi-square, and then the degrees of freedom is 9 minus 3, because we had 9 classes, but then again you can actually reduce that. And then you will see that we have the 3 parameters, the sample size, and then mean and standard deviation. So I should say standard deviation as well, not just the mean. And STD, we use that in the normal distribution. So previously we used, so in the normal distribution we use that. So 9 minus 3, 6 degrees of freedom I used. So you can see that 6 degrees of freedom, and then if you go to the chi-square table, you will see that that's the chi-square value we have from the table. If you compare them, then you will see that it's actually falls within the acceptance region. That means we actually cannot reject the null hypothesis. Then we can say that we cannot say that it doesn't follow. That means actually you can say it follows the normal distribution. So you can say we use the same formula, and then the degrees of freedom will be changing, and you can use the chi-square table so that you can find them. So the last one is the test for independence. It's really simple. You will see that we have 2 factors, and then we would like to find these 2 factors we have, whether they are actually dependent or not. In this example, you can see that we have 200 random samples. 200 random samples, we divided them into 2 factors. So you can see that we have number of trees, and a number of trees by species. That means Douglas fir, hemlock, cedar, and then the level of decay. So you can see at first no decay, minor, major. So 3 kinds of or levels of decay. So we want to test whether decay and species, these 2 factors or 2 kinds of variables we have, they are actually independent or not. The null hypothesis is they are independent. The alternative is that they are dependent. So at first, what we need to see in this data set is that you can see we have the observed data. So 9 observed data set, that means total number of trees in each of those cells. and then all we need to do is that we have to sum them. Let me draw. So you can see that the actual table is from here up to here. So that's the actual table. So all we need to do is to find the row total. That means sum them, sum these three values, and then also you need to find the sum of the column total. Okay, so we can find the 6 totals in here. So you can see that we also have the grand total in here. So that means you can either sum them, sum the row total, or sum the column total. Either way, it will be the total number of trees we have. That means the sample total. Okay. After that, so all we need to do is that since these are observed value, that means in the chi-square test, the observed value, these are the 9 observed values we have, and then we have 3 rows, 3 columns. So that means we have 3 by 3 contingency table. That's what we call. So to find the expected value for each of these values, that means each 9 values, let's say each of these values, we need to find the expected value. That means we need to create another table, and then in that table, let's say we have Douglas fir, we have hemlock, and then cedar, then no decay, and then minor decay, and then major decay. Let's say minor and then major. Okay. So for 39 observed value, the expected value, this is the expected table EI, this is the observed table OI, and then for 39 all you need to do is to find where we have the total. So you can see for 39 we have the row total is 132, the column total is 50, and grand total is 200. These are the 3 values we need to find the expected value for 39. So that means we have to multiply 132 by 50 and then divide by 200. Then you will find that the expected value for 39 is this one. Similarly, let's say for 10, we need to use 28, the row total, column total is 80, 28 multiplied by 80 divided by 200. Then you will see that the expected value for 10 would be in here, and then you can easily find that. For each of those cells, you need to find the expected value. So the row total and column total, we basically call them marginal values. That means we have to use the marginal values so that we can find the expected values. So that's how for each of these observed value, you can see in the bracket we wrote down what's the expected value we found. That means for 9 of those values we have the expected values. Now you can actually create a table and say that for 9 of those observed values, what are the expected value. That's what I showed you before. So I created a table for each of those observed value. We have the expected value. Then we can find the observed minus expected, and then take the square and then divide each of them by their corresponding expected value. Basically we are trying to find this one, and then if you sum them, sum all the values, then you can find the chi-square statistics value. So that's how we found this chi-square value 5.8. And then previously I showed you how we calculated found the critical value from the chi-square table. But in here, all you need to do is to find the degrees of freedom using this one. That means how many rows you have minus 1 multiplied by how many columns you have minus 1. In the table we have three rows, 3 columns, right? So that means 3 rows minus 1, you have to multiply that by 3 columns minus 1. That means you have to multiply 2 by 2. That means you have degrees of freedom 4. That's why we say that degrees of freedom you have to use 4. The level of significance, it's given or not, you can choose 0.05 if it's not given, and then you can find the critical value and compare it with the chi-square statistic value. Since this is a one-sided test, and you can see that it's already in the acceptance region, that means we failed to reject the null hypothesis. So that means they are, what do you think? They are independent or dependent? They are, we can say that they are actually independent. That means there is no dependency going on based on the hypothesis test we performed. So there is one more consideration. Whenever you will see that you have 2 by 2 contingency table, that means 2 rows, 2 columns only, then you have to go for one more step. So you need to use this formula. So you can see that observed minus expected, and then you have to take the absolute value minus 0.5 and then square that. That means previously we just used observed minus expected, but over here, since we have 2 by 2, 2 rows, 2 column, then you have to use that correction. So another thing you have to consider is that if any expected frequency find is less than 5, then we cannot perform this test. That means this test will not be valid. So you will see that in the textbook we have some examples. Also in the assignments I gave you a test so that you have to perform, and then maybe in the exam you will see a similar problem sets. So that's it about the test of independence. And then I already talked about goodness of fit. Previously you saw the test for variance, one single variance or multiple variance. Thank you.